The only rocks that geologists can study directly are those of the Earth's crust. But the Earth's crust is a thin skin of rock, making up less than 1% of total volume of the Earth. In fact, scientists are not able to sample rocks very far below the Earth's surface. Some deep mines penetrate 3 kilometers into the Earth, and a deep oil well may go as far as 8 kilometers beneath the surface. The deepest scientific well in Russia has reached only 12 kilometers. But Earth has a radius of about 6,370 kilometers. So, it is obvious that geologists can only scratch the surface when they try to study directly the rocks beneath them. So, how to study the inner layers of the Earth? The molten material brought to the Earth's surface through volcanoes give geologists a glimpse of what the underlying layer might look like. The meteorites also provide clues about the possible composition of the core of Earth. Apart from this, the deep parts of the Earth are studied indirectly through the branch of geology called geophysics, which is the application of physical laws and principles to the study of the Earth. Geophysics includes the study of seismic waves and Earth's magnetic field, gravity, and heat. All of these things tell us something about the nature of the deeper parts of the Earth. Together, they create a convincing picture of what makes up the Earth's interior. In this video lesson, you will learn how seismic activity helps us understand and describe the inner layers of the Earth. Seismic waves from a large earthquake may echo through the entire Earth. A human-caused explosion also generates seismic waves. But how are these seismic waves used to help us visualize the subsurface? One important way of learning about the Earth's interior is the study of seismic reflection, which is the return of some of the energy of seismic waves to the Earth's surface after the waves bounce off a rock boundary. If two rock layers of differing densities are separated by a fairly sharp boundary, seismic waves reflect off that boundary just as light reflects off a mirror. These reflected waves are recorded on a seismogram, which shows the amount of time the waves took to travel down to the boundary and return to the surface. From the amount of time necessary for the round trip, geologists calculate the depth of the boundary. These reflected seismic waves can be used to image geologic structures deep within the crust and the mantle that are not exposed at the surface. Another method used to locate rock boundaries is the study of seismic refraction, which is the bending of seismic waves as they pass from one material to another with varying density. This is similar to the way that light appears to sharply bend a straw resting in a glass of water. As a seismic wave crosses from one rock layer to another, it changes direction as shown in this figure. This change of direction or refraction occurs only if the velocity of seismic waves is different in each layer. Do remember that, in contrast to seismic reflection, sharp rock boundary is not necessary for the refraction of seismic waves. An earthquake produces several different types of seismic waves, which can be broadly divided into two categories: the body waves and the surface waves. While the body waves travel through the Earth's interior, the surface waves travel along the ground's surface. Surface waves are important, but they don't provide much information about what happens below the surface. For this reason, we need to study the body waves so that we can see what Earth's inner structure is like. The body waves are of two types: the P waves and the S waves. The P waves are called primary waves because they are so fast that they are the first waves to reach an observer at a seismic station after an earthquake occurs. The P wave can move through solid rock and fluids like water or the liquid layers of the Earth. As shown in this picture, it pushes and pulls the rock it moves through. The second type is the S wave or secondary wave, which is the second wave you feel in an earthquake. The secondary waves are slower than the primary waves and can only move through solid rocks, not through any liquid medium. It is this property of S waves that led seismologists to conclude that the Earth's outer core is a liquid. The S waves move rock particles up and down, or side to side, perpendicular to the direction that the wave is traveling in. Since the seismogram records the velocity of movement of the body waves through the Earth, we can tell what type of material they are traveling through. As the body waves travel through the Earth's internal layers, their speed changes, causing the wave to bend. It was the study of these seismic refraction and seismic reflection techniques that enabled scientists to plot the three main zones of the Earth's interior. The crust is the outer layer of rock, which forms a thin skin on the Earth's surface. Below the crust lies the mantle, a thick shell of rock that separates the crust above from the core below. The metallic core is the central zone of the Earth, which is also the source of the Earth's magnetic field. Studies of the seismic waves have shown that the crust is thinner beneath the oceans as compared to that of the continents. Besides, the seismic waves travel faster in the crust below the oceans than in the continental crust. Because of this velocity difference, it is assumed that the oceanic and the continental crusts are made up of different kinds of rocks. This is also found that the seismic P waves travel faster through the oceanic crust as compared to the continental crust. Since the velocity of a seismic wave is related to the density of the material, it is considered that the oceanic crust is denser and heavier than continental crust. The oceanic crust is mostly made of basaltic rocks, whereas the rocks that make up the continental crust are less dense and heavier than the basaltic ocean crust. Granite is a mineral that's a major component of the continental crust. Do remember that the oceanic crust may be heavier and denser, but the continental crust is a thicker and older part of the Earth's crust. The next layer is the mantle, which lies between the upper crust and the lower core. Since both the secondary and primary waves pass through the mantle, geologists think that the mantle is also made of solid rocks just like the crust. The boundary that separates the crust from the mantle beneath is called the Mohorovi discontinuity. So, we can say that the Moho discontinuity marks the lower limit of the Earth's crust and beginning of the mantle. Since the velocity of the seismic waves in the mantle region is little higher, the scientists have concluded that this region must be relatively denser than the crust, and also the composition of rocks would be quite different. The mantle is further subdivided into the upper mantle and the lower mantle. The best hypothesis that geologists can make about the composition of the upper mantle is that it consists of ultramafic rocks such as the peridotite. The crust and the uppermost mantle together form the lithosphere, which is considered as the outer shell of the Earth that is relatively strong and brittle. Generally, seismic waves increase in velocity with depth. But you can see in this figure, the increase in velocity of the seismic waves with depth is not uniform. In this figure, the velocity measurement starts from the crust portion and it increases with depth. But at a depth of around 70 to 125 kilometers, the velocity decreases and then again it starts increasing as we go deeper. So, this zone has been called the low velocity zone, which is a part of the larger layer called the asthenosphere. This asthenosphere is the zone of the Earth's mantle, lying beneath the lithosphere, and it is believed to be much hotter and more fluid than the lithosphere. Since the lithosphere has a lower density, it floats on top of the asthenosphere, similar to the way in which an iceberg or a block of wood floats on water. In the lower part of the asthenosphere, that is about 300 to 700 kilometers depth, the velocity of the seismic waves gradually increases. Compared to the asthenosphere, the lower mantle below the asthenosphere is more rigid and less plastic. At the top portion of the lower mantle region, there is an abrupt increase in velocity of the seismic waves, which indicates the sudden change in the properties of the rocks on entering the lower mantle. We can also observe here that, through the depth range of 700 to 2,900 kilometers, there is a gradual increase in the velocities of the seismic waves. Next is the core of the Earth. The seismic wave data provide the primary evidence for the existence of the Earth's core. It is observed that the seismic waves from a large earthquake do not reach certain areas on the opposite side of the Earth. As shown in this picture, an earthquake occurs on one side of the Earth and is recorded by a seismograph on the other side. From this figure, you can see how the primary waves spread out from a quake until at 103 degrees of arc from the epicenter, they suddenly disappear from seismograms. It is found that at more than 142 degrees from the epicenter, the primary waves reappear on seismograms. So, the region between 103 degrees and 142 degrees, which lacks the primary waves, is called the P-wave shadow zone. The P-wave shadow zone can be explained by the refraction of P waves when they encounter the core boundary, deep within Earth's interior. As you can notice in this figure, the Earth's core deflects the primary waves and casts a shadow, where their energy does not reach the surface. In other words, the P waves are missing within the shadow zone because they have been bent or refracted by the core. We have already discussed that while the primary waves can travel through solids and fluids, secondary waves can travel only through solids. Let us now have a look at this figure, which shows that an S-wave shadow zone also exists and is larger than the P-wave shadow zone. The S-waves are not recorded in the entire region more than 103 degrees away from the epicenter. The S-wave shadow zone seems to indicate that S-waves do not travel through the core at all. If this is true, it implies that the core of Earth is fluid by nature. After carefully analyzing the way in which P waves are refracted within the Earth's core, the scientists propose that the core can be divided in two parts, that is a liquid outer core and a solid inner core. The boundary between the outer core and the mantle is marked by great changes in seismic velocity, which implies there are abrupt changes in density and temperature of the region. This transition zone, which is up to 200 kilometers thick, is known as the D layer, where the velocity of the P waves decreases dramatically. The seismic and density data, together with assumptions based on meteorite composition, point to a core that contains iron and nickel, with at least the outer part being liquid. The existence of the Earth's magnetic field also suggests a metallic core. Of course, no geologist has seen the core, but since so many lines of indirect evidence point to a liquid metal outer core, most scientists accept this theory as the best conclusion that can be made about the core's composition. So, this is how the seismic waves provide crucial data about the internal layers of the Earth.